Hello everyone, this is Dr. Amir Maharjan. So on this video, I will be solving some circuit problems using various techniques. But I will just get started with some simple problems, something called a voltage divider circuit, which you often need in the lab. So voltage divider circuit is so in this example, as you can see, two resistors are connected in series, and then power supply battery is connected, and the battery voltage will be divided into two resistors, and that's why it is called a voltage divider circuit. And it's a very useful circuit in everyday circuit, because let's say if you need only 3 volt in any given electronic circuit, but if the battery voltage is 9 volt, let's say, so how do you get 3 volt out of 9 volt? Then you will have to construct a voltage divider circuit. That's why it is a very useful circuit. So in this problem, so here's the problem. So you have two resistors in series, connected in series, and a battery, a 12 volt battery is connected across the series resistance of R1 and R2, and the given resistors are 220 kilo ohms, and the second resistor is 500 kilo ohm. So these are the given values. So the very first question is, calculate the actual or theoretical voltage across the second resistor R2 if the voltmeter is ideal. So a voltmeter is connected across the second resistor, and it's asking if the voltmeter is ideal, then what would be the voltmeter reading? So that's the question. So, and if you remember from the lecture slide, an ideal voltmeter would have infinite impedance, right? Infinite internal resistance. So it doesn't draw any current, so it won't affect anything. So let's solve this problem. So since it's a voltage divider circuit, two resistors in circuit, so first your job is to find the total current through the circuit. And as you know, since both resistors are in series, the current will be same everywhere, right? Because there's no other alternate branches. So the current will be, so the total voltage in divided by the total resistance, and the total resistance is R1 plus R2, because the two resistors are in series, right? And so it's 12 volts divided by, so first I'm gonna solve it in terms of symbols, and then we will put the numbers. And so we're solving V2, which is the voltage across the second resistor, right? I will be same, IR2, just Ohm's law, right? So I is V in divided by R1 plus R2 times R2, right? So then you can say V2 is going to be R2 divided by R1 plus R2 times the total battery voltage. So this you can directly use if you have a voltage divider circuit anywhere, and if you want to find the voltage across this second resistor, it will be just like this formula. And if you want to find the voltage across, let's say voltage across the first resistor, right? So V1 will be then from the same technique. So it's going to be R1 divided by the total resistance, R1 plus R2, times the V in, right? So let's solve this problem. Let's find out the actual numbers, because that's what we're supposed to do. So you're given all these numbers. The battery voltage is 12 volt, and it's asking what will be the voltmeter reading. The voltmeter is connected across the second resistor, right? So V2 is going to be R2 divided by R1 plus R2 times V in, and so R2 is 500 kilo. So let's keep everything in kilo ohms, as long as the all the resistance units are same, they will cancel out anyway. So 220 kilo ohms plus 500 times the battery voltage is 12 volts, and that should be ideally, right? If the voltmeter is ideally, the voltmeter will read that much voltage. And let's do the calculations, and that's going to be, so 500 divided by 220 plus, okay, 8.33 volt, right? If the voltmeter is ideal, so in principle this voltmeter must read 8.33 volts, right? And the rest of the voltage will be dropped here across R1, right? So that's it. So this is simply called a voltage divider circuit, right? And if you want to find the voltage across the first resistor, then you can do the same analogy, right? So V1 will be R1 divided by R1 plus R2 times V in, right? So R1 is 220 kilo ohms, so 220 plus 500 times 12 volt. So V1, it's not actually V1 in this particular problem, but let's check. So 220 times 12 divided by 220 plus 500. So 3.66 volt. And as you can see, so we'll talk about this in Kirchhoff's law anyway at some point. So the sum of the voltage V1 plus V2 has to be 12 volts, and which is what we see, right? And that has to be true, right? The battery voltage is 12 volt, which is divided into these two resistors. So that's why it is called, this simple circuit is called a voltage divider circuit, right? That's the part. This is the first part. Now the next part gets interesting. Now it says, now if the voltmeter used in this measurement, given voltmeter, right, placed across R2, let's say it's not ideal, let's say, right? It's not ideal. And let's say that this voltmeter has some internal impedance or internal resistance of 10 mega ohm. Now what would be the voltmeter reading, right? What would be the voltmeter reading if the voltmeter is not ideal? The voltmeter has some internal impedance, internal resistance or impedance as 10 mega ohms, right? So what would be the voltmeter reading? So let's do that. Now what's going to happen is, if the voltmeter has some finite resistance, if this voltmeter has some finite resistance, then the second resistor will see some parallel resistance in parallel with this, right? So now the voltmeter resistance and R2 will be in parallel, and that will decrease the effective resistance here, and that will decrease the total resistance, that will decrease the total current, and everything will change. So let me redraw the circuit again. So this is your battery, and this is your first resistance, this is your second resistance, right? So R1, R2, they are same. It's 220 kilo ohm, this is 600 kilo ohm. I'm sorry, if you what would be the percentage difference in the voltmeter readings if you use two voltmeters? Okay, so it's actually you use two voltmeters, one having 10 mega ohm, very high impedance, and one having only 600 kilo ohm on the same circuit. R1 and R2 are same, right? 220 and 500. So first, let's see. The first one is let's use a voltmeter having 10 mega ohms, right? So let's solve this problem. So now this 10 mega ohm will be in parallel with R2, right? So what would be the effective resistance here? This effective resistance in this branch will be R equivalent, right? I'm going to say R2 equivalent will be, so this is in parallel combination. So one, I'm going to keep everything in kilo ohms. So 1 divided by 6, I'm sorry, that is 500, is the original. 500 kilo ohm plus 10 mega ohms means 10,000 kilo ohms. 10,000 1000, and there's a inverse. And let's find that out first. 1 divided by 500, 1 divided by 10,000 kilo ohms, and it's inverse. So I have 476 kilo ohms as the effective resistance. So you can clearly see the effective resistance has decreased. Now do the same thing. Now your equivalent resistance R2 is this. So what will be the voltmeter reading then? So V2 is using the same voltage divider circuit, right? So R2, now you have to say R2 equivalent, right? Divided by R1 plus R2 equivalent times V in, right? Let's put all the numbers. So R2 equivalent is 476 kilo ohm. So R1 is still 220 kilo ohms plus 476 kilo ohm, right? Times the 12 volts. The battery voltage is still same. Now let's do that. So 476 divided by 220 plus 476 times 12. So 8.2 volt, right? Not very different from 8.3. So theoretically, in principle, right? In principle, it should record 8.33 if the voltmeter is ideal. But if you use a voltmeter with 10 mega ohm internal resistance, it will record 8.2 volt. Still not that bad, right? Now the next question is, now you use a second voltmeter whose internal resistance is only 600 kilo ohm. So what would be the new voltmeter reading now, right? Let's repeat the same technique, right? So your first job is to find the R2 equivalent, the new R2 equivalent, right? This R2 equivalent. Now you have a voltmeter whose internal resistance is only 600 kilo ohms, which is comparable to 500 kilo ohm, right? And if that's the case, then it's gonna be a big problem. So that we will see, right? And this is still 220 kilo ohm. Okay, let's find the R2 equivalent resistance, and that's going to be again the parallel combination. So this R2 will see this 600 kilo ohm as a parallel combination, right? So 1 over 500 kilo ohm plus 1 over 600 kilo ohm inverse. So let's find the equivalent resistance of that. 1 divided by 500 divided by 600, and that's going to give me only 273 kilo ohms. So as you can see, the equivalent resistance R2 has significantly dropped, right? Almost half, right? And now what would be the new voltmeter reading? If you use this voltmeter having only 600 kilo ohm impedance, so then use the same thing, right? Same voltage divider rule. R2 equivalent divided by R1 plus R2 equivalent, and it's V in, right? And let's put all the numbers. So R2 equivalent 273 divided by 220 plus 273 times 12. So 273 divided by 220 plus 273 times 12 volts. That's going to give me only 6.64 volts, right? And you can clearly see a huge difference in reading. It's supposed to ideally, right? Ideally, it should read 8.33 volts, right? As you can see, we saw from the first part. Now, but it's only reading 6.64, huge difference, right? And it's because of this shunting. This is called shunting effect, because now the voltmeter is not ideal. It has only 600 kilo ohm, which is very low in terms of impedance, right? Which is comparable to the second resistance 500 kilo ohm, and that's why it's reading really low voltage than it's supposed to. So what is the percentage difference then, right, between the actual and the reading? Is 8.33 divided minus 6.64 divided by the original and times 100%. It wants you to find the percent. Alright, this percentage difference in the voltage measured by the voltmeter having low impedance is going to 8.33 minus 6.64 divided by 8.33, and it's 20.3% off, right? So if you use a voltmeter having 600 kilo ohm as internal resistance or impedance and connect it across this second resistor 500 kilo ohm, which is comparable to this, right? This voltmeter will read a voltage which will be 20% off, right? It's supposed to read 8.33, but it's only reading 6.64 volt, right? And it's 20% off, right? Remember, when you use a voltmeter with 10 mega ohm impedance, internal resistance, which is much greater than this resistance, the voltmeter reading was not very off, right? It was not significantly off. It's a little bit different. But if you use a comparable resistor, right, internal resistor having comparable resistance, so its reading will be significantly different. And this defect of voltmeter or any instrument is called something called loading effect. So this effect is called loading effect of a voltmeter, right?